Today we'll discuss the two predominant learning methods, supervised and unsupervised learning, and introduce the two most common machine learning tasks, classification and regression. Our objectives today are to understand the concepts of supervised and unsupervised learning and distinguish the two, and understand the learning tasks of classification and regression and identify the goals of each. Most learning problems can be broadly separated into two large categories, supervised and unsupervised. Supervised learning has underlied the success of many deep learning applications and will be the predominant focus. However, it is worth mentioning unsupervised learning to clarify the distinction between the two methods. We begin with supervised learning. With supervised learning methods, our goal is to learn a mathematical function that best maps our input data to its respective target label or value. In supervised learning problems, each example in our data is already assigned a target label or value. This allows the mathematical model to compare its predicted labels or values to these ground truth targets, and make the necessary parameter updates to more closely match prediction to target. We are already somewhat familiar with this concept. Recall our radiology resident in the last video. They were given a stack of chest radiographs to classify as normal or abnormal, and they also happened to have available all the true classification labels for each radiograph in order to compare their predictions to the ground truth. Let's briefly discuss how data is generally structured in a supervised learning problem. Note that there are specific data structures which are best suited for particular tasks and deep learning algorithms, which we'll cover in more detail later. For our radiograph classification task, how might we structure our data? Recall that big X denotes the entire dataset. We have multiple training examples in the dataset, with each example denoted by little x. The superscript number in parentheses simply denotes a particular example in our dataset and should not be confused with exponentiation. Here, for example, we're talking about the second example in our training set. If we're talking about some arbitrary example, we can call it the ith training example, with I short for index. Each example has a number of features. Since we're using image data, the features are pixel values. We can pack these features into a column vector, with each element of the vector representing a particular feature. The number of features is denoted by the symbol n subscript x, pronounced nx. M is used to denote the total number of examples. Thus, the last example can generally be denoted by a superscript m in parentheses. Matrix dimensions are conventionally reported as rows by columns. Thus, our matrix here is an nx by m-dimensional matrix. Now, each example in our dataset is assigned a label, in this case, normal or abnormal. These labels are contained in another matrix denoted big Y, which is an ny by m-dimensional matrix. Ny indicates the number of labels per example. M again indicates the total number of examples in our dataset. Since for this particular problem, each example in our dataset is only assigned a single label, this would be a 1 by m dimensional matrix. So we've discussed both the supervised learning method and the general form in which data is structured for this type of learning. Let's now move on to unsupervised learning. In distinction to supervised learning, in unsupervised learning, our data is not assigned a known target label or value. The objective of unsupervised learning is finding structure in unlabeled data. The goal of such problems may be to discover groups of similar examples within the data, called clustering, or determine how the data is distributed, a process known as density estimation. Or perhaps we wish to project the data from a high-dimensional space, which we have trouble visualizing, down to 2 or 3 dimensions so that we can better visualize it. This is a process called dimensionality reduction. Let's go over a simple clustering example. Our radiology resident is now given a stack of chest radiographs that are unlabeled. The task is to review the images and cluster those with similar features into distinct groups. For simplicity's sake, we'll cluster them into 2 groups. While the resident does not have access to target labels, they are still able to recognize similarities and differences between images and group them into individual clusters appropriately. Note that the resident is not ascribing any label or intrinsic meaning to the clusters. The clusters simply indicate groups of similar data. Clustering and other supervised learning tasks give rise to many interesting applications and questions, but will not be further discussed for now. So we've discussed the two predominant types of learning. We will now discuss the two most common supervised machine learning tasks, classification and regression. In classification tasks, Our goal is to predict a label for every example in the dataset from a discrete set of classes. We've already had some exposure to classification tasks through our earlier radiograph classification problem. Classification tasks are subdivided according to the number of classes we have to choose a label from, in addition to how many labels we can assign a given training example. For instance, in binary classification, each example is assigned a single label, of which there are only 2 classes to choose from. In multi-class classification, each example is once again assigned a single label, but we now have greater than 2 classes to choose from. For example, normal, heart failure, pneumonia, or other. Finally, in multi-label classification, each example is assigned 1 or more labels, and we have greater than 2 classes to choose from. Note here how some examples have been assigned several labels, for instance, pneumonia and heart failure. Moving on to regression tasks. In distinction to classification, in which the predicted output was 1 or more discrete labels, the goal of regression is to predict the value of 1 or more continuous output variables given the value of 1 or more input variables. We will not cover the individual types of regression models in depth, but some are presented here for a quick overview. Regression tasks can be subdivided based on the number of input and output variables. The simplest example is that of simple regression. Using 1 input variable, we try to predict the value of 1 output variable. For example, using age to predict systolic blood pressure. Tasks which relate 2 or more input variables to a single output variable are termed multiple regression tasks. In multivariate regression, 1 or more input variables are used to predict 2 or more output variables. Regression tasks can also be subdivided based on the mathematical relationship between the input and output variables. Recall that the relationship between input variables to output variables may either be linear or nonlinear, which gives rise to the terms linear and nonlinear regression. Finally, more modern regression approaches such as lasso, ridge, and elastic net regression use techniques to prevent data overfitting, a process called regularization. In summary, we've introduced the concepts of supervised and unsupervised learning and distinguished the two, and we've also explained the learning tasks of classification and regression and have identified the goals of each.